and we'll start at 1 o'clock. The top of the hour, whatever it might be for wherever you are. Okay. Hello, everyone. I'm Dave Woon, the Secretary of the Astrochemistry Subdivision. This is another of our grad student organized AstroCheminars. I'll be passing things off to them momentarily, and they will run the rest of the AstroCheminar. I have a couple of quick announcements. We are very close to announcing the winners of our 2024 competition for the dissertation prize. Hopefully that'll be, we'll hear about that soon. The other piece of news is that our next symposium at an ACS meeting will be in March 2025, and it will be a meeting in honor of Eric Herbst. I see that Eric is in attendance. All of us who are involved in this are very much looking forward to a chance to honor Eric Herbst. Okay, so now I'm going to pass things off to Catherine and Athena and Kate.
Thanks. So thank you for the introduction. My name is Catherine. I'm use she, her pronouns, or any pronouns. I'm a third-year PhD student at the University of Wisconsin-Madison, studying under Professor Susanna Wickes-Weaver. And Kate and Athena, you can also introduce yourselves.
Thanks, Catherine. I'm Kate Gold, also a Catherine, and I use she, her pronouns. I study under Dr. Lucy Zuri, doing observational work, mainly on our Arizona telescopes on Kitt Peak and Mount Graham through the University of Arizona.
And I'm Athena Flint. I'm a third year, although I guess we're all rising fourth years, at the University of Mississippi under Dr. Ryan Fortenberry. I've been doing some reaction pathway stuff computationally on some inorganic species, but I've also done work on C3H2, so I'm really excited to hear what Divita has to tell us today.
So if you haven't attended one of these graduate student run seminar series before, just an overview of what we're trying to do here. We're really looking for a way to showcase astrochemistry research through these AstroCheminars, with an emphasis on graduate students and early career folks in astrochemistry, with a focus on wanting to provide a platform for networking, for knowledge exchange, that we can all sort of share research journeys and career paths and life experiences. So if this is a program you are interested in giving a talk for, or you have other ideas, please just email us directly. Our emails are on the website where you registered. So with that, thank you for coming. Kate, can you talk a little bit about the Q&A and introducing our speaker?
Yes, of course. So today we're going to be focusing on a presentation by Divita Gupta titled High Resolution Spectroscopy of Astrochemically Relevant Ions. And our speaker today will talk about her experience in this field, and we welcome all questions. We leave it up to the speaker's discretion whether they answer questions throughout their talk or at the end. Or the focus at the end. But please do raise your hands or leave questions in the Q&A box below so that we can answer your questions. Additionally, you can find contact information, as Catherine mentioned, so that if you'd like to get in contact with any of the organizers or additionally any speaker, you also have that opportunity. And one way that you can do that, I'm not sure if the chat is available to you, but we have just listed the astrochemistry subdivision website, http:// and the slashes astro.phys-acs.org. And so you can find more information there about our program, and in case you would like to join us for our future events as well.
All right. So our speaker today is Dr. Divita Gupta. Dr. Divita Gupta completed her dual bachelor's and master's in chemistry from the Indian Institute of Science Education and Research in Mohali, India in 2018. She then joined Professor Ian Sims for her PhD at the University of Rennes, France. She worked on obtaining low-temperature reaction rate constants essential for accurate astrochemical models. She was awarded the 2022 Snyder Astrochemistry Award and the Best Thesis Prize from the RSC Spectroscopy and Dynamics Interest Group. Her thesis work also received a special mention by the International Astronomical Union Division B. She is currently working as a Marie Curie postdoctoral fellow with Professor Stefan Schlimmer on high-resolution spectroscopy and low-temperature reaction kinetics of ions in Cologne, Germany. Dr. Divita Gupta's talk is titled High-Resolution Spectroscopy of Astrochemically Relevant Ions. So with that, please take it away.
Thank you so much, Catherine and Kate and Athena. Let me get my pointer in. Thank you so much for the kind introduction. And hopefully today I can excite you about what I've been working on over the past 2-something years now, where I've been exploring the high-resolution spectroscopy of astrochemically relevant ions. So I am a very astrochemistry person. I love astrochemistry and everything about it. So today the focus would be just ions, so reactive species, and looking at the spectroscopy. Okay, so ions are actually known to be quite ubiquitous in the cold interstellar medium, with around 15% of the 300 plus molecules detected in the interstellar medium are actually ionic species. Most of these are cations, as you can see over here. Most of them are cations with a very small fraction of anions as well, which are mostly long carbon chains. And of course, detected in Taurus molecular cloud, which is a very cold molecular cloud. But even within the cationic species, you can really see there's a diversity of different kind of molecules. You can see one example with the phosphorus. You can also see a cationic fullerene, but even smaller molecules, there's a lot of them. You can see diatomic, simple polyatomic molecules. Then you also have ions containing halogens, and then you have hydrocarbons, a lot of nitrogen containing, oxygen containing, sulfur containing, and even magnesium containing ions. So you can see that within the inventory of the molecules that we have, which have been detected in the interstellar medium, a large variety of them are actually ions. And even within the ions, you do have a lot of diversity. And ions really are quite a crucial part of the astrochemical reaction network. As an example, you can see image that I took from Brett McGuire's review article from 2018. Where you can see that the ions actually can be involved in these, in the cold environments, can be involved in cold neutral reactions. So they can have a lot of proton transfer reactions to then form these complicated molecules. And these ion neutral reactions can be quite important for these cold environments because they remain fast. So because of these electrostatic interactions and long range interactive forces, the ions and neutrals, when they interact even in cold interstellar medium, the reactions will remain barrierless and will remain quite fast. So they can really increase the chemical diversity of the species present in these cold interstellar environments. More than that, they can also be used by astronomers and astrophysicists as tracers, or some of the ions can be used as tracers in a lot of the UV-rich environments, like a Horsehead Nebula over here you can see, which is a very well-known photodissociation region, and also in diffuse clouds. So the idea there is that by looking at the ion and the parent neutral species, you can understand how much the cosmic reionization of the different astrophysical environments can be. But to be able to get the abundances of different ions and to know which ions are present in which environments, we do need high resolution infrared and microwave spectra of these ions to allow their detection. And that is what we are trying to do here at Cologne. And that's not all. We are also actually looking at a lot of other reactive species like radical, where we're looking at the microwave spectra using chirp pulse. We are also looking at neutral molecules using absorption setups. And many of you might already know the Cologne database where all the spectroscopic information is available. But today, like I said, I will only focus on the ions. And for studying the ions, we are actually using action spectroscopy. So this is one example of the setup that we have available. And you can see this is the ion setup that I'm talking about. So, and this part over here is just lasers. So over here, what we have is a 22-pole ion trap setup, where we then employ action spectroscopic method. And then in combination with high resolution OPOs and quantum cascade lasers, we are able to get this high resolution spectroscopy of ions. And this I will now start talking more about in detail about the different aspects of this. So first, to do spectroscopy, we need ions, and we can't really buy ions in a bottle because they're quite reactive, of course. So what we do is we actually generate these ions in situ. So we actually have an ion source, which is a storage ion source. So you kind of put in your neutral precursor. In this case, could be acetylene for the molecules that I am interested in. We put in acetylene, and then you have these the heated filaments, which will then eject electrons, and via electron impact ionization of this neutral precursor, you can form ions. This ion source itself is also a storage ion source. That means you can actually store these ions for a few seconds, which allow them to also form further reactions, and then you can kind of increase the complexity of different ions that you can form. And you can imagine that by having them in storage for some time, you can really increase the different chain reaction that you could have, and then you can end up forming a lot of different hydrocarbon ions in here. But we don't really mind that, because we do have a mass filter, which is a quadrupole mass filter, which actually allows us to select which mass of the ion to charge ratio which actually go through this mass filter and then is bended in and enters the trap itself. This trap is really the heart of the machine that I'm talking about. And this is a 22-pole ion trap. The design for this was developed quite some time ago. And actually the application of these ion traps towards low temperature ion chemistry was initiated or pioneered by Dieter Gerlich in 1980s, 1990s. But the idea in these 22 poles is you can see there are 11 poles over here from one side and other 11 coming in from the other side. And you basically can apply an oscillating electric field, which can be used to capture the charged particles inside here in the radial direction. And these ion traps are actually quite small. So you can see a comparison with the two European euro coin over here, which is basically, I would say, still like $1 something. So similar sizes. And this all is then housed in a copper housing that you see over here. So this trap is really a very small component, but is really the heart of the machine because it allows us to contain and trap the ions inside the species, where we can then probe them using our lasers and do their spectroscopy. So not just the radial confinement, for the actual confinement over here, we also have two DC voltages. And to see how they are applied, you can imagine that we have a trap, and then within the copper housing, we are also actually cryogenically cooling it down to a temperature of roughly 4 Kelvin. So the idea is that if you think about the kinetic energy distribution of your ions, it will look something like this, where your x-axis, you have the kinetic energy as a function of temperature, and then you have the probability of how many ions would be there at a particular kinetic energy. But the idea is that if I can set my DC voltages or this difference in such a way that it is much higher than what the kinetic energy of the ions are, which are actually quite cold, then none of the ions can basically escape out in this direction. So you're basically confining them in this axial direction based on their kinetic energy, which is quite low because we are cryogenically cooling it down to 4 Kelvin. And then once our ions are now trapped inside here, we can then probe them using the light source. So how do we do then the spectroscopy of the ions? If you think about a classical absorption spectroscopy measurement, you can imagine your your molecular sample over here. You have your light going in, and then some of it, as compared to the resonant frequency, will be absorbed, and the rest will be emitted out. In a traditional method, what you can imagine is that you would look at the change of this light. you would see which frequency has been absorbed and where the photons have changed to get the spectrum of this molecule that you're looking at. While this is really nice, for ions, this can be quite difficult because it's really difficult to produce ions in sufficient amounts because, like I said, they're quite reactive. So the moment you try to form them in large quantities, they will actually just react away. So you can't really have a lot of them. And also, since generally they can be quite hot conditions, so it can be difficult to sustain them as well. So what we do instead is we don't look at this remaining photon. What we look at is the change on this molecular sample itself due to the absorption of photons. And this way of doing absorption spectroscopy is also known as action spectroscopy, because you're not looking at the change in the photons or the light itself, but rather change in the molecular sample. And this is quite cool and can actually be quite useful for ions because ions can be counted quite sensitively. So if I was counting my number of ions and something changed in this ions, I can actually detect that change quite precisely. So what change can we actually induce to these ions depending on the light source? So while there have been many action spectroscopic methods which have been used previously, today I'll just talk about this method called leak-out spectroscopy, which has been developed in Cologne over the past couple of years, led by Philip Schmidt. And the idea here is that once you do have your mass-selected cold ions, they can then be excited by an infrared laser. And of course, if I'm talking infrared, I'm talking about the vibrations of molecules. So if I was to then hit this molecule or this ion with a resonant frequency, a photon, that it will actually excite this molecule vibrationally, what can happen is now this ion has extra vibrational energy. So while this is great, the vibrational energy doesn't really help us quite well. So what we instead do is we actually have it colliding with another neutral buffer gas. So what we can have is this excited vibrational molecule can actually collide with the neutral buffer gas. And this collision is quite useful because it will allow having the internal vibrational energy transferred into the kinetic energy of both these species. So suddenly the internal vibrational energy of this ion is now, via this collision, transferred into extra kinetic energy for this ion itself. And to put it into perspective, when I do have my ions which are trapped over here, now suddenly some of the ions which were much lower kinetic energy can indeed escape out of this barrier height that was set up. So you have some ions which, depending on what the frequency was and if they were actually vibrationally excited, can then leak out of the trap and they can be detected. So essentially, you are increasing the vibrational energy by a resonant photon, which then collides with the neutral buffer gas, allowing for a transfer of energy from internal vibrational energy to kinetic energy. And with this kinetic energy, you can actually have the ion leaking out of the trap, which can then be again filtered and counted using a Dali detector. And this can be done quite sensitively with an accuracy of even 1 to 2 ions. And this is what you would get. You would get almost background-free signal when the frequency was not resonant, but when the frequency is indeed resonant with this vibrational excitation, you start to see more ions leaking out of the trap, and that is how we can record our spectrum. So this is quite cool. So now we can actually look at mass-selective cold ions and look at their vibrational spectroscopy. So the idea was, which ions do we want to look at? So when I started, I wanted to look at more hydrocarbon ions, and the hydrocarbon ions are actually quite useful because we all hear in astrochemistry a lot about polycyclic aromatic hydrocarbons, their photodestruction, the top-down, the bottom-up approach. But the idea is, if we are able to detect hydrocarbon ions in the interstellar medium, it will actually tell you about how much their photodestruction is in a particular region, versus how much they can actually further form bigger polyaromatic hydrocarbons. So one of the species that I did look at was cyclic C3H3+. This is actually quite well known to be an important transient species in the astrochemical reaction network, especially since it is known to form via C3H+, which has already been detected in PDRs. And it can react with H2 to form C3H3+. And also we know that cyclic C3H3+, with its electron recombination, can actually form this neutral molecule, which has been detected in a variety of different interstellar medium. So So this has been detected, this has been detected. So the next species of interest was this ion itself. So this is actually quite exciting also from a chemistry side, because this is a smallest aromatic hydrocarbon cation, so quite exciting, aromatic. But also just spectroscopically, it is a symmetric top. So you can imagine how the spectrum would look like. And in this case, we did probe the mu4 fundamental stretch, which is the CH stretch that you can see. So it's an antisymmetric stretch where two hydrogens are coming out, one is coming in. And the idea here was that we can actually use a high resolution OPO laser to look at the rho vibrational features. So this is an important point to note, because I've talked about with the loss technique or the leak out spectroscopy technique, we are exciting the molecule vibrationally. But since we do have very high resolution lasers, we can actually even probe the rotational levels within these vibrational levels. So what we are getting is not a broad vibrational spectrum, but rather very high resolution rho vibrational spectrum. So when we did do that for the cyclic C3H3+, this is the spectrum that we got, which you can see in white. And this lasts over more than 30 wave numbers. And this whole measurement was really just done in 2.5 days of measurement, and 2 days, maybe half a day of setting up and everything, but just 2.5 days of complete measurement, which is really cool. And this you can actually see with our simulation fits quite well. And while this all might look like a stick spectrum, this actually is quite detailed, as you might also remember from a couple of previous slides. And there are a lot of different points coming in. So they are very high resolution data under all of this. So this was actually not the first measurement of this mu4 rho vibrational spectrum for this molecule. This was also measured by the Linnartz group in 2014, where they did look at cyclic C3H3+, and they used a lean and helium, and they did a discharge experiment. And their rotational temperature is reported to be around 35 Kelvin, and they used cavity ring down spectroscopy. So as you can imagine, since they're using a discharge experiment, they also produce a lot of other hydrocarbon ions. So they do not have the mass selectivity, but it's still quite impressive that they were actually able to assign, by using different control experiments, they were able to assign which features could be coming from this specific species itself. And they were able to assign about 130 assigned lines itself. It's quite sad, I have to say it, like about Harold Linnartz. It's really a shame, because he was really a great experimentalist. But we have been able to improve this now by assigning over 300 lines. And this experiment, of course, like I mentioned, has been done under cryogenic conditions, where the rotational temperature in this case is around 40 Kelvin. Of course, we're using leak out spectroscopy. And since we do have the mass selectivity, we are quite consistent and quite sure about the features that we are seeing are actually coming from this molecule. So there's no real control experiment that we have to do in terms of assignment for the molecule itself. But also the features, if you remember the previous slide, do match a symmetric top quite well. So with this, we're actually able to get a very nice fit of our spectrum of our rotational constant itself. As you can see, also the B constant is a very nice number. If you are a math nerd like me, I think 1 wave numbers is also quite nice, because then you have a 2B spacing in your spectrum, which would look something like this over here, you can see. And if you're very particular, this is actually just 1 wave numbers, rather the 2 wave numbers is this, the 2B spacing, and that's just because you also have the delta K selection rules apply in for a symmetric top, and that's why you have this half a wave number here, which is coming in from your C constant. So it's actually a pretty neat molecule just in terms of pure numbers. And this actually matched quite well with not just the Linnartz work, but also the computational study which had been done in the group of Professor Timothy Lee, who also sadly passed away last year. And all the measurements agree quite well, not just for the rotational state, but also with the first excited vibrational state for this mu4 fundamental band. So while this is all very cool, the rho vibrational spectrum can indeed be used for infrared search. If you think about ground-based telescopes, what you would really like is a rotational spectrum. However, this molecule does not have any dipole moment, so it will also not have any rotational spectrum. But still, this measurement was quite helpful with validating theory from the Timothy Lee's group. And then what can be useful is that they also use the same quadric force fields to also derive constants for the deuterated versions of this molecule itself, which they have reported in 2011. So now we can actually start with their predictions for the deuterated molecules. And we actually chose the singly deuterated cyclic C3H3 plus molecule. The main reason just being the dipole moment was quite favorable. So if we were to look for it in space, dipole moment will certainly help us. The dipole moment for this molecule is quite high. It is, in fact, although asymmetric top, so the spectrum is not that pretty, depending on your definition of pretty, I guess. So it looks like quite complicated, but still having the initial guesses from or predictions from the computational model did quite help us when we looked at the mu1 symmetric CH mode for this molecule itself. This work has already been published last year, so you can look more for the details for this one, because I will not talk about the rho vibrational spectrum. But what I would rather like to talk about is the rotational spectrum. So like I said, with just having the rho vibrational spectrum, we can still get a very good fit and the predictions for the ground state and the vibrational excited state rotational constants. However, the accuracy that is required for astronomical searches can be quite high. And just based on the rho vibrational transitions, we can be off by 5 to 10 megahertz, or at least a few hundred kilohertz, which is not really sufficient for an astronomical search. So what we would have rather liked to do is actually measure a pure rotational spectrum. And now we have to go back to our experimental figure, where if we look over here, and we talked about the leak out spectroscopic technique, and the idea there was that the vibrational energy and then converted into kinetic energy allows the ion to escape out. While this works for vibrational energy, because the vibrational energy gaps can be quite high, it does not quite work the same way for rotational energies because they can be quite small. So what we instead do is we use a double resonance technique. So what we have here is, while we had our infrared source, we also have our millimeter wave source going into our trap as well. And then what we will look at is if I'm looking at my ground vibrational state. And here just the labels is, since it's an asymmetric top, you have the J, which is the rotational level, and then you also have two projections, Ka and Kc. But let's just look at the J levels. So if I was looking at my ground vibrational level, and I wanted to look at the difference between the J5 and J6, I can't quite probe it using directly leak out spectroscopy. But I can use a line which is interlinking my vibrational level to this ground level. So while I cannot directly probe this one using leak out, I can focus on this yellow transition, which is going from the ground vibrational state into the high excited, first excited vibrational state. And this is how my signal would look like, where at the right infrared frequency, I would see my ions which are leaking out of the trap have increased. And now if I was to focus and fix my laser at just this top point or the peak of this IR transition, I would just see a single line or a ion count of something like 1,000 constantly coming out. But if I were able to change the population of this low level for this vibrational transition, I can actually change the intensity of my infrared line itself. So if I was to actually pump this J equals to 6 by pumping this right frequency from J5 to J6, I can actually increase the signal of this infrared transition itself. And that's what we do. So we tune our millimeter wave source, and then we can actually see that when I'm hitting this right frequency, which is actually increasing the population of J6, I can actually see an increase in my infrared signal itself. And that is how we are actually able to get the rotational frequencies for these molecules. So we are not applying leak out directly, but by using a double resonance, because you're creating this double resonance, because you're kind of finding a common level in between this vibrational levels, and we can use that to actually also get the right rotational frequencies. And we did do this for cyclic C3H2D+, and we were able to get about 15 or 13 rotational lines for this molecule, which have also been reported in the paper last year. So now this is great because this can actually now be used to directly search for this molecule via radio astronomy. Unfortunately, we were not so lucky, because based on some density estimates by Yuri Aikawa, and then also discussions in-house with Peter Schilke and also with Brett and Pepe Chanicharo, we were actually able to see that it will either require thousands of hours of integration with the IRAM 30-meter source, or require for the L1544 source, and for the TMC1, there were no lines which could be really detected up to the sensitivity of 0.15 to 0.2 millikelvin, which is a shame, of course, but at least we do have now a good starting point from astronomers that maybe in the future they can actually see this molecule in the space. And it's also quite interesting because it's a deuterated molecule, so it could actually be also used maybe as a proxy to get back to the cyclic C3H3 plus abundance as well. So it could be quite exciting in the future. But we didn't stop there. We also then looked at another molecule, which is the linear version of the same C3H3 plus. So this is the almost linear version. So it's not really a linear molecule that like you would imagine. So the spectrum is not really 2B spacing, but it's almost prolate asymmetric top, almost a prolate symmetric top. So the spectrum still has a nice pattern to it, as you can see over the 2B spacings roughly over here. It does have a Q branch. And this work was actually led by Wesley Silva, who's also a Humboldt Fellow in the group over here. And then we were actually able to also use the same technique that I mentioned with the double resonance technique to get the rotational spectrum, which was then great because it does have a very favorable dipole moment, about 0.55 dBi. And while we measured the 14 rotational lines in lab, one of them and then plus 3 lines were actually detected in the torus molecular cloud using the Quixote survey led by Pepe Chanicharo. So this molecule is actually present in the torus molecular cloud, a picture of which you can see over here, which was quite cool because now this allows us to understand this important species, which is quite well known in astrochemical reaction data networks. And then now it provides an upper limit for the abundance of the species, and of course, then help tune out the astrochemical databases. Okay, now for the next part, I will actually move my focus slightly away from spectroscopy, pure spectroscopy, but rather I will focus on using spectroscopy as a tool itself. So while leakout is quite cool and quite universal to look at the rho vibrational spectrum and then in combination with double resonance, look at the rotational spectrum of ions, it also provides us this unique opportunity to explore the different spectral features between structural isomers and nuclear spin conformers. So what do I mean by that? So if you imagine a trap, if I'm talking about the C3H3+, what I said to you before is that we do have a quadrupole mass filter. So while I do have the mass selectivity for C3H3+, it also has 2 structural isomers. So when I do have a mass selected sample, I will also have 2 structural isomers which are in the same mass, which I cannot really distinguish or can't really escape from having in my trap. So when I have my trap with C3H3+, I have both the almost linear or the open chain version, but also the cyclic version. But the frequencies where these molecules are excited or the rho vibrational transitions are really still very unique to each individual molecule. So I can actually use that. So if I were to now use just a transition of one of the species, so let's say H2C3H+, so the almost linear chain over here, what I can do is if I'm using a transition for this molecule, over time, when I started with something like 1,000 ions, if I keep pumping the molecule or that transition, at some point, most of my molecules or the linear version or the open chain version will actually leak out of the trap. So I will actually have lost all of my linear version if I keep pumping with the same rho vibrational transition frequency. And over time, all I would be left with over here is the cyclic C3H3+. And by looking at how much this depletion was, I can actually tell how much the amount of this isomer there was to begin with, which is really cool. So now I can actually understand how much of the different mass or structural isomers there were inside the trap. And also prepare a clean sample of just the cyclic, which is left then inside. But our life is slightly complicated because, as you can imagine, for water, you have these 2 hydrogens, and the 2 hydrogen nuclei and its spins can actually orient themselves in 2 different ways. So you can actually have two different nuclear spin conformers, ortho and para, and the statistical weights for water are known to be 3:1 for the ortho and para. And you can imagine if I just flip my molecule like this and have these two hydrogens, the nuclear spin weights for this molecule are also 3:1. But these two nuclear spin isomers also behave like quite separate species because we do not have any extramagnetic field in our, so we are not interconverting them. We're also not having any secondary reactions which could interconvert them. So what was to start with ortho H2C3H plus will remain ortho and the para will remain para. And they also have different spectral features which we can then exploit. So if I was to pump just ortho H2C3H plus, I can actually see that over time, I lose my molecule over here. And what I'm left with is something like, by looking at this percentage depletion, I can actually get something like 12%. I can do the same for also para, and what I get is something like 4%. This is quite consistent with an error for 3:1 ortho to para ratio. We then also did this, I also did this for cyclic species, where I could get an ortho to para of 1:1, which is also quite well reported. So overall, if I had my sample, in this case, I had acetylene as my precursor, I can actually tell that I had only 80% of the cyclic isomer to begin with. And within this, I had ortho and para as 40 and 40%. And for the linear or the open chain version, I had 20% of it. So this is quite cool. So I don't just get the percentages, but like I said, I can also prepare now nuclear spin and isomer specific mixtures in my trap, which can then be used to also study many reactions, which I will not talk about today, but it's quite exciting. Just to summarize, the Lika spectroscopic technique at the 22-pole ion trap setups that we have in Cologne can be quite sensitive and selective. And also with the leak out spectroscopic technique, it is also a very universal action technique. And since we do have cryogenic cooling, we also have the advantage of having very, if you remember looking at the spectrum, the lines are very narrow because we have very narrow Doppler widths. We don't really have pressure broadening because our pressures are quite low. And also having these low temperatures also provide favorable partition functions by limiting the level, the rotational levels which the molecule has access to and can be easier to assign then. Also with the powerful OPOs and the quantum cascade lasers that we have in Cologne, we can actually collect high resolution low vibrational spectra in the range of over 2000 wave numbers from 1500 to, so from 3 microns to almost 7 to 9 microns. And when combined with millimeter wave sources in a double resonance scheme, we can actually also collect very high resolution rotational spectra of these ions, which, to be very honest, can be a slower process than measuring the vibrational spectrum, but still quite useful. And both of them can combine, can be used for astronomical searches of these ions. And in the second part of the talk, like I mentioned, the unique ability of kicking out specific structure isomers and nuclear spin conformers are now allowing us to prepare clean samples, so not just mass selective, but also isomer and nuclear spin selective samples. And then the long interaction times in the trap. Since we can trap our ions for about tens of seconds, we can actually then look at the reactions of these isomer specific and quantum state specific species. And all of this is quite, the fun part is that you're not really using huge amounts of precursors because the ion number that we have are only up to 10,000. This is, if you think about the Avogadro number, that's 10 order of 23. And if I'm only talking 10 power 23, 10 power 5 or 10 power 6, that's not really a large amount of precursor I have to use. So we can have gas bottles lasting us for almost decades, which is really cool. So with that, I would like to thank all of you for coming. And of course, my group, Professor Stefan Schlemmer, who has been really the guiding light in all of this, and the funding sources and the ACS subdivision for inviting me, Dave, Kate, Catherine, Athena, thank you so much. And I will look forward to the questions. Thank you so much.
Thank you, Dr. Divita Gupta. Thank you so much. So we'll be taking questions now. It looks like there are already a couple questions in the Q&A box. But as a reminder, you are welcome to put questions in the Q&A or in the chat. And if you would rather ask your question using your microphone, please raise your hand and we will unmute you. So first off, Lucci asked why 20-something poles are needed in the 22-pole ion trap, since typical ion traps usually contain just 4.
It's a very good question. So that is true. You can use, of course, a quadrupole as well to trap your ions. I don't really have, I think, a backup slide for it. But what you would end up having is you would have a lot of RF heating then. So you will actually suffer from a lot of the heating effects. So your ion temperature will actually kind of quite increase. And that's why we're not really using it. And even in case of 22 pole, to be very honest, I did mention 4 Kelvin. The rotational temperature that ions usually do have, even if the cryogenic temperature is 4 Kelvin, is still of the order of 10 Kelvin to 15 Kelvin. And even at 10 Kelvin or 40 Kelvin, like you saw, the spectrum can be quite complicated. So we do want to go as low in temperature. So we're really limiting the rotational levels and also, to be honest, the Doppler widths, so that we can avoid a lot of the overlap and then allow us to kind of assign easier for these ions, which can still have very complicated spectrum, even at low temperatures. And these are still like easy examples. You can still have a lot of the torsional, like high torsional systems where it really gets quite crazy. So the idea is that we want to avoid most of the RF heating effects, which you would really have in quadrupoles.
Thank you.
Yeah, thank you so much. Oh, thank you so much for the answer. I see another question in the chat from Ryan Fortenberry, who asked, what difference between quantum chemical and referring to computational fundamental techniques and those from experiment are useful for your interpretation of the experimental spectra? And a rephrase of that question, in other words, what do you need from theory to help you?
Hi, Ryan. Nice to see you here. So I think with what we have and given the time that we have right now with laws and how fast it really can be, even if we are off by 10 or 15 wave numbers, I would say we are still pretty okay. Generally, we do start with 40 Kelvin so that we do see some higher J's. So we can kind of already start seeing parts of branches. So even if we are off by, let's say, something like 10 to 15 wave numbers in terms from the predictions, it's still okay because we can start, and then within a couple of days, you would still kind of get to the right Q branch or the P and R branches for these molecules. It can, of course, be different for different molecules because these are still, I would say, relatively simple molecules. If you're talking about more complicated molecules like H5 plus and like more torsional affected systems, then I would say it's a different story. But just for these simple systems, generally 10 wave numbers, 5 to 10 wave numbers is pretty good. And I think with your calculations, you have it. So it's generally not that off.
Great, thank you. Isel Cook asks, are there any prospects for searches for C3H3 plus with JWST? And fantastic.
Hi, Elsa. So I've had discussions with Partha Bera from NASA Ames about this because I think they were trying to search for the cyclic species, at least with the Sophia telescope. Now that's out of the window. But I think with JWST, I can't say I have a clear answer because I think with JWST, the abundance of the species could still be quite low, I would say. So it could still be quite complicated. But also, I think purely in terms of looking at exoplanetary atmospheres with JWST, I think they're also looking for very high temperature constants, which are still not there. So we can still have like second order distortion constants from these fits, but we don't really have then the next order fits. So I think we would still need to improve a little bit, but I think it's still a good starting point. But I think we would still need to then go higher temperature to look for high warmer environments at least. But for the cold environment, I'm still unsure about the sensitivity with JWST and the predicted abundance for this molecule. I think it could be still challenging, but hopefully in the coming decades.
Yep.
Thank you. It looks like there's another question in the chat from Lee Q. I wonder if the speaker has opinions on advantages of doing this experiment with single molecular ions.
That's a good question. Because I know that the group of, getting the name now, UC Santa Barbara, they have looked at single ion molecular spectroscopy. I think just in terms of the leak out method here itself, I think the number of ions do give us the capability of leaking them out, and then kind of like, because every cycle we are repumping it, so we are leaking it out and then looking back at it. So I think it does also give us some intensity information in that terms, but I'm not quite sure if I have enough knowledge about the single molecular ion spectroscopy measurements to really say much on it.
Thank you. We do have plenty of time for additional questions if anyone has other questions. In the meantime, I might ask a personal question. If you had to give advice to, us rising fourth-year grad students, what would your advice be? What can we do? What, not to think of regrets, but if you had regrets from grad school, what's your recommendation to us or your past self?
I can't really complain about grad school because my grad school experience was really, really fantastic. Even though there was COVID in the middle, I had great mentors in Elsa and also Ian Sims. So I had a really nice environment all around me. I think the main thing which actually made my experience so fun was talking to people and reading a lot. So I think staying curious really was the key for me, for example, because you have to ask stupid questions. You have to assume that even if people think you're asking stupid questions, that's completely okay, because that's just the way you learn. And I think that continues on, like even as a postgrad now, like postdoc now, I think sometimes I remember like in the beginning, I would feel like, oh, I can't really ask this question because maybe I should know it. But I think it saves us so much time. And if you have a nice environment around me, why not just ask those stupid questions and increase the pace of your learning? So yeah, just I think ask questions, read lots of papers. Like for me, I think like I said, I think my interest was so heavily into astrochemistry. I love talking to astronomers. I love reading astronomy papers. I love looking at different kind of experiments just to kind of understand what all is happening around me. And then, but yeah, I think if you love research, I think you just have to stay curious and keep asking stupid questions, keep reading. I think that really has been the key for me, at least.
Thank you.
I think Lu Chi jumped in with one last question. Oh, Kate, were you getting around to that? They had one last question, wanting to know what the range your current QSL laser can cover.
So the quantum cascade lasers, we do have multiple of them. So of course, not all of them can cover 600 wave numbers. So we actually have different quantum cascade lasers, which then cover different regions. So I know there's one from 1950 to around 2050 or so. So I think each of the lasers roughly covers around 100 wave numbers, but we do have different ones. So we have one around 1300. So we have one around 1600. 1700. So I think, so we don't have one quantum cascade laser, that's why every time there was an S. So there are multiple lasers which allow us to then kind of cover this almost complete range. There are still some gaps, but roughly we can cover all the way down to 1500 wave numbers, 1300 wave numbers, but there's no one laser which covers everything.
Awesome, thanks. And then there's one more that got just dropped by Holdson Liang. Was mentioning, yes, your talk today was aimed at the ions you were looking at, but will there be anything on the line of sight method be done differently if we are looking at radicals?
That's a really interesting question. I think the moment why we are right now looking mostly at ions is just because we can so sensitively measure ions itself. So if we did have to go to radicals, I think the idea there would be we are looking at an ion signal which is changing or an extra kinetic energy which is given because of this excited radical. So there would be like an indirect method, because you can't really quite capture the radicals the same way. So even though they are reactive and have unpaired electrons, they're still not quite charged. So you can't really control them or trap them quite well you can't really trap them with this insider trap. So there are some ideas, I think, kind of how to use them by coupling with the ions, but they're still very, I think I would say early phases. Maybe Stefan Schlemmer has better ideas, but I think it's still very early phases. But there could be a way where you could look at the vibration of radicals in relation to the ion. So you have to still make a change in the ion number itself, though, because we can only really trap and then sensitively count our ions and not quite radicals yet, unfortunately.
Thank you. If there was time, I actually had one more question of my own. Because I love cyclopyrrolene and C3H2, but I've never really focused on the ions. But there was kind of a lot, there was a window where there really wasn't any work done on any of those species because it was thought of as a dead end in chemistry. And I was wondering how you thought perhaps your work, or if we even like found some of these other species, might contribute to strengthening a discussion of how C3H2 or the ion itself might participate in broader hydrocarbon chemistry.
That's a very good question. And I don't think I have a clear answer for it. I think, so for me, the interest really stems from this big gap between these small ions and the big ions. And as I think also as a chemist, I'm also looking at more aromatic and like cyclic species. So for example, like if you look at this C3 chain right now, we know in Taurus molecular cloud, for example, we do have C4 and C5, C7, but at some point they have to start turning, right? So I think it's really important to capture that point of turn, and when things are trying, because we know there's benzonitrile, we know there's benzene, we know there are cyclic species, we still don't know any small heterocycle or smaller aromatics like cyclic species. But I think there has to be a linking point, and that's where my interest really comes from. I think if we can identify these in between, like not so small and not so big molecules, and have a good luck, like we also might, like I think if they're still slightly almost linear or slightly curving in, the dipole moment still favors us in terms of detection. So I think having upper limits on their abundances can be really, really crucial. So I do think like then identifying these in between parts can be quite important. And that's kind of where my interest stemmed for, to kind of go from these. And that's what I've also continuing to work on partially here as well, is like looking at slightly bigger carbon chains and then kind of starting to see when because also in this case, for example, you have the cyclic species and you have the almost like the open chain version. Energetically, the cyclic one is actually more stable. But we also produce enough of the open shell, and of course, there's enough of the open shell that open chain that it was detected actually in interstellar medium. But if the moment you actually even go to C4, the cyclic version is actually quite unstable. It's not unstable, but it's like less stable than the open chain version. So I think there is like this trend which starts to follow in, and I think that's where my interest kind of stems in. Like, when will it happen? Then it kind of reverses back, and the cyclic one might become more stable. And looking at and getting like some upper, I think, limits for the abundances, I think, just to understand and limit the astrochemical network, I think can be quite crucial. I hope that answers your question.
Yeah, it did. Thanks. And I'm not seeing any other questions in the chat. Did either you, Kate, or Kat have any other things you wanted addressed?
There's one more question.
Just got one, yeah. Right, Tristan, did you want to take that?
Yeah, so Stephen says, thank you very much for the presentation. Because of the peculiarity of our country, I may only be able to carry out computational approach to study the interstellar medium. I would need some certain guide to enable work of my thesis. And if I could get your mail to share my work with you, that would be really awesome.
Of course, I'm very happy to have any conversation about astrochemistry or just ions and computations. Of course, we still like computations. They do help us kind of not having to look at this wide range of everything. So yeah, I think if you just put in my name and Cologne, I think you might be able to get to my email ID or at least my website, and then feel free to email me, and then I'm happy to chat more.
Great. All right, I think maybe we can sign off early then if no one else has a question. All right. Thank you again, Dr. Divita, and thank you, everybody else for attending. And have a great rest of your day.
Thanks again for coming, sure. And thanks for everyone for coming in attendance. If anyone has any speaker recommendations, we're always interested in showcasing speakers, showcasing their research, and showcasing their experiences, as they are people, you know, within all of these academic institutions. And so if you have a self-recommendation or a nomination of someone else, please do reach out to us if you're interested in serving as a speaker, or inviting one of your buddies to be a speaker as well. We're always interested in showcasing the brilliant people around us.
Perhaps.